Right, so this is the second talk about the lowRISC project. Oh, too loud. So here I'm talking about what we have implemented to support the tag memory. And recently we have published a release on our first stage or preliminary support for tag memory. You can see the address on the bottom of the slide. I need to say that the work is still ongoing, so we need to do a lot of optimizations and more features in the future. So right now it's only a proof of the concept release. So, well, Alex has said a lot about lowRISC yesterday, so I just briefly remind it. So lowRISC is an open source project which provide open source SoC for people to use. The two features we try to provide for people is one is the minion core, the other one is the tag memory, and obviously I'm talking about tag memory for this talk. The tag memory I'm meaning for tag memory here is we add tag bits for every word. We do it on word level. So we add configurable number of tag bits for every 64-bit word in all cache lines and memory. There are a lot of use cases for tag memory. For example, if you use the tag memory to protect your security, for example, against the control flow hijacking, you can set the permission bit in the tags. Therefore, if the permission is lack permission, then means some code is going wrong, so you can kind of protect your code. The other one is, it's also possible that you put locks in the tags, that then you have quite lightweighted synchronization method for memory, shared memory. And recently we have MPhil students doing on garbage collection that he finds out we can put the types or status memory into the tag bits, which could help to do a precise garbage collection and speed up the garbage collection. And the final one is we think the tag bit could be used to put some breakpoint into it. That means you get lightweighted breaking point, definitely you get infinite breaking point, something like that. This is not an absolute list of what we can do. There are other use cases we can explore. So what we want is general purpose tag memory support. And here shows you my understanding of the memory hierarchy of current Rocket chip. So the Rocket chips have multiple tiles. Each tile has a Rocket core. It also has its own private I cache and D cache. The L2 is currently banked, so you could have multiple bank L2 caches. The L2 caches and L1 caches are communicated using crossbar right now. There's only one memory controller currently, so there's the access or request from L2 caches are arbitrated through the arbiter and will go through a tile link IO to memory IO converter and finally goes to the memory controller. So here is how we do it to support the tag cache. As I have said that we add configurable number of tag bits to every 64-bit word. What we do is we extend the cache line in L1 D cache and L2 cache, and we put the tag bits directly at a higher bit level of the every word. We found this quite easy to do for load and store tags in the instruction support. And thanks for the easy to do that in Chisel or in current Rocket core, we found basically we haven't changed anything in the L2 control logic. It's totally transparent, and the current L2 can handle the extended cache line. We choose to use a separate memory partition to store the tag bits instead of using ECC, as we found it gives us more general support for tag bits. For example, we can support an arbitrary number of bits, and we don't rely on changing the memory controller to support tag bits. But that brings us a problem because for the memory controller, if we want to access the memory, we need to access the data and the tag as well. That means we double the traffic rate to the memory controller. We need to access data and access the tag at the same time. To reduce this memory traffic overhead, so we add a tag cache in between the L2 cache and the memory controller. This cache will only cache the tag bits. So if there's a hit, we don't need to access the memory controller, kind of save the traffic. And on the instructional software side, we added two instructions currently. They are load tags and store tags. So basically what they do is you specify an address and the two instructions will load the tag bits to a general purpose register and will store the tags from general register to the tag field in your cache line. It uses the normal RISC-V format, so basically what I need to do is add two instructions in the control pipeline, and I haven't done any other change, just add another memory type. So when the L1D cache receives this request according to type is no, it's actually looking for a tag, so the tag will go through the L1D cache to RISC file or RISC file to D cache. Also, we have noticed that the memory controller have a long latency but have a large bandwidth. So it can support multiple requests to memory controller. That's why we have implemented multiple trackers that to support concurrent requests from L2 to memory controller to kind of reduce area memory access latency. So as you can see, adding the tag cache support in current Rocket chip is quite easy. We choose to use a non-intrusive way to do it. But currently it's not efficient, so we have a lot of work to do. I will talk about this later. To test the functions of the tag support, we have choose a lot of ways to try to find bugs, and currently may still have bugs. One way we do it, we implement, we add some head files to add the instruction into inline assembly code. So we can use this inline assembly code as a C functions. Therefore, we can do C program to test the tag cache. We also reuse the RISC-V test repos to do bare metal test. And we use the C program to memory sweep, do a large-scale tag testing. We also boot Linux on a FPGA. Currently, it's the Z board. So we can see that the thing is working at least. Also, we have done a unit test using System Verilog to do random testing for the tag cache itself. It's also public. It's also available on a separate branch of our code release. To test the performance of our tag support, we have managed to compile and run 9 of the 12 SPEC 2006 integer benchmark cases on FPGA, the Z board. So here is the result. As you can see that, well, what I have done is we add a hardware performance counters in different level of caches, L1D cache, L2 cache, tag cache, so we can get all the miss rate and traffic to memory. The miss rate is the unit of misses per 1,000 instructions, and memory traffic is in unit of transactions per 1,000 instructions. And the first 3 columns show you the miss rate of I cache, miss rate D cache, miss rate of L2 cache. And the 4th column shows you the memory traffic when the tag is not used. So it's the memory traffic for original Rocket chip. Then the rest of the table shows you the miss rate and the memory traffic for 4 different kind tag cache. They have different sizes from 16 megabytes to 128 megabytes. Basically, you can see that the miss rate and the traffic will reduce by increasing the size. There are 2 interesting cases. One is MCF, which always has a large memory traffic. The other one is SPECint, as no matter how we increase the tag size, the missing rate in tag cache is still significant. So what I do, I kind of put these 2 cases on here, and along with the average case. The figure on the left side shows you the memory traffic. Actually, the memory traffic is here is kind of normalized, so it shows you the ratio compared with the tag cache, compared with the one doesn't use tag cache. So in perfect situation that we could get a ratio kind of near to 1, that means the tag cache doesn't increase much traffic. Right side figure shows you the actual absolute number of memory traffic of the different cases. So as you can see that MCF cases is always get much large memory traffic, but actually the traffic ratio will follow the average cases that increase in the size of tag caches, it will decrease. For the SPECint, although the tag traffic ratio is always significant, but actually the real memory traffic is small, so it really doesn't count. Well, I don't want to make an assumption that our conclusion is to increase the tag size to kind of reduce the missing rate. The purpose of the figure is just show you that tag cache can work. We want to do more optimization, so basically we don't need to increase tag cache to reduce the missing rate. Sometimes we can do others to reduce the area overhead, even using small tag cache to get the same missing rate. So for example, we have certain ideas on this. We notice that sometimes program doesn't use tag caches, program doesn't use tags at all, or some cache line doesn't use tags. So if the program knows that a page doesn't have tags, so it can set a bit in the page table and say this all the memory address in this page table will not kind of bypass tag cache and it will save traffic. The other one is tag cache in itself can automatically detect whether or not the cache line has tag bits. If they found the tag bits is always 0 or not used, basically this cache line can be identified in a bitmap, say it's always bypassed. Also, sometimes even with a dirty cache line, we found that tag bits may not be revised. So if the tag cache detects that the tags are not really revised, it will save the write back stage. That means the tags won't be write back to memory. And to support the general purpose tag cache, we need to add more support in the instruction level. Like we found out sometimes we need to load the data and the tags automatically, and to support the breakpoint debugging, and to support production of control flow hijacking, we need to add tag bits in the I cache and add some checks for the instruction whether or not they have sufficient permissions or there's a broken point in there. Also, we found sometimes it's convenient for us to have instructions to set or clear the tag bits for a whole cache line. So the final stage is if we want to support general purpose tag cache, we need to have a kind of method to translate or interpret the purpose of the tag caches. But sometimes we need to allow the tags to go through the pipeline stages and allow some mechanisms to translate what kind of tag interpretation you want. We may also support storage like a fixed table or using a minion core to control the minions of those tags. Well, so basically, in this release, we have add tag support for current RISC-V rocket chip. It's a preliminary support, so there's a lot of work to do in the future. Right, thank you.
Tariq Afzal, LG. What was the organization of the tag cache, and was there any aging?
Pardon, could you say it again?
What was the organization of the tag cache? Is it a full associative cache? Or?
It's a set associate, currently using the same structure as L2. So it's an 8-way, it's a 64 SAT to 512 SAT. So basically it's configurable, it's a set associate structure.
And how do you replace a tag?
How do I replace tag?
Yeah.
I don't quite get it, but so the tag cache only stores the tags. When there's a request from L2, it will using the address to figure out whether or not there's a hit in the tag cache. And if there's a hit, it will kind of fetch the data from cache line. That's a normal cache.
Adam Nackley, Google. When these tags are used for permission checks or breakpoints or something, isn't there a danger of breaking assumptions that existing software has, i.e. the kernel reads from a user space buffer and then the user space has set tags on this and now the kernel faults, or shared memory between processes and such?
Well, it could be right, but what we want is to provide a mechanism you can choose to use or not. So if the kernel field is like you would say, then it's a choice. We provide choice for users. Doesn't necessarily say you must use it.
Oh, very short. Can be short. First, 64-bit data. What's the size of tag?
Currently, we implement 2 bits or 4 bits. It's reconfigurable. The maximum bit currently supported is 8 bits.
Okay. Then what's your reason to put a separate? You put save the tag and the data in separate place?
That currently is convenient because we want to change a lot of code in current RISC-V rocket chip, but definitely we can do it in another way. So we can put all the tags in the end or higher bits of the cache line, or even put tag bits into a separate cache.
So your tag don't have ECC protection?
We can add that, yeah.
Okay. Okay.